Hello friends, I have discussed about all the chapters so far except permeability and effective stress. So how to find out the effective pressure? That's a very important term and very important in geotechnical engineering because the strength of the soil mass is a function of effective pressure and not the total pressure. And the settlement is also a function of effective pressure. So it is very important to know about the effective stress value. I will take one example. For example, let's take a ground surface. So this is the ground surface. And let's say this is fully saturated. If it is fully saturated, naturally the the unit weight as gamma saturated, and let's say at a particular depth the column of the soil, if I take it, the soil column, its weight will be acting at its CG. So this is the soil column which I am going to consider. So how much will be the weight? If the cross-sectional area of this soil column is going to be, the area is going to be A, and the height is taken from the ground surface up to this bottom of this soil column, and let's say this is equal to Z, then what is the total weight of this soil column? So the total weight of the soil column above A, say this is A, so above A will be how much? What is this area of this soil column? Let's say the area of this soil column is A. So this is the cross-sectional area of this soil column. So A is the area multiplied by the height Z will give you the volume of this soil column. If you multiply it by gamma saturated, that becomes the total weight of this soil column. Now this total weight divided by the total area of this soil column will give you the total stress value. So total stress sigma at A will be the weight of this soil column divided by area of this soil column. So this then that means area and area will get cancelled and you get gamma saturated into Z. So total stress at any point is going to be gamma saturated into, that means what is the total unit weight multiplied by the height of the soil column above that particular plane, that is going to be the total stress sigma. So we can say the total stress sigma above any plane or above any point is the total unit weight multiplied by height of the soil column. Very simple way you can find out the total stress value. So total stress value sigma can be computed. But you know that the strength, the shearing strength of the soil mass is a function of effective stress and not total stress. So what is that effective stress? Now if I put a piezometric tube at this A, let's say I insert a piezometric tube over here, then because the soil is fully saturated, the water will rise up to the ground surface. So this is the water level in the piezometric tube. This is the piezometer. So if you insert a tube at A, the water has risen up to the ground surface, and this ground surface is going to be the height of water above point A, which is equal to Z. So therefore the pore water at A will be unit weight of water into height of water column above A. So this is going to be gamma W multiplied by ZW equal to Z. So therefore, pore water pressure is given by this. And you know that if you want to find out the effective stress, that is sigma prime, so at any point A, the sigma prime at A will be equal to the total pressure at A minus pore water pressure at A. Therefore, it is going to be equal to total pressure is already known to you. This is sigma. So sigma equal to gamma sat into Z. So you write it gamma saturated into Z. This is the saturated soil mass. So gamma saturated into the height of the soil column minus the pore water pressure is gamma W into Z. So Z can be common. So it becomes gamma sat minus gamma W into Z. Therefore, effective pressure at A will be gamma submerged multiplied by Z. So it is the submerged unit weight into the height of the soil mass. So this you can find it out. This is how you can find out for fully saturated. Say the condition is such that the ground condition could be like this also. So this was one of the condition. You can find out the effective pressure at any point, and if the ground condition is like this is the ground level, and you have got the groundwater table GWT, groundwater table at a certain depth, and you want to find out at A. Now if you know the total unit weight above the groundwater table, let's say it is gamma T. And this height, let's say it is Z1. And below the groundwater table, the soil is naturally fully saturated. So the unit weight is going to be, total unit weight is going to be gamma saturated. And this height is, let's say, Z2. How will you calculate the total pressure sigma? So total stress sigma at A, if you want to calculate, how will you calculate it? It is going to be equal to gamma T into Z1. So gamma T into Z1 plus this part Z2, the condition is it is fully saturated. So gamma saturated into Z2. This is called the total stress. At any point you can calculate it. At any level you can calculate it. So at this level, this is going to be the total stress. What is the pore water pressure at A? So pore water pressure at A will be UA. Now, if I insert a piezometric tube over here, so you have a standpipe that you have inserted at A. So in this piezometer, the water will rise up to this level, up to ground level. Isn't it? Therefore, the pore water pressure is unit weight of water, gamma W, into height of water column, and water column is Z2. Therefore, the effective stress at A, sigma prime at A will be sigma total pressure at A minus pore water pressure at A. That is the relationship. So this is the relationship for effective pressure at any level. So this we have already found out. That means it is going to be 1 minus 2. So it is gamma T Z1 plus gamma sat Z2 minus the unit weight of water into Z2. Therefore, it is going to be gamma T Z1 plus gamma sat minus unit weight of water into Z2. Therefore, the value of effective stress at A can be simplified as sigma prime at A equal to gamma T Z1, gamma T Z1, and this is underwater. So, gamma sat minus gamma W will be gamma submerged, that is submerged unit weight, or gamma prime into Z2. So this is the final. Now let's say the water table during monsoon, it is going to touch the ground level. So I will take this condition now that the groundwater table is going to touch the ground level. So my groundwater table is now touching the ground level itself. So GWT, groundwater table, is going to touch the ground level. So at any plane A, which is at a depth, say Z, how will you calculate the total pressure? The total pressure sigma, what is the unit weight it is? The total unit weight is gamma saturated. So it should be gamma saturated into Z. And the pore water pressure here will be gamma W into the water column will be up to Z. If you insert a piezometric tube, the water table will be up to Z. So therefore, the effective pressure at A will be gamma sat minus gamma W into Z. That is gamma prime into Z, where gamma prime is the submerged unit weight. It is called submerged unit weight. So you can calculate like this. Now let's say the ground is flooded. The case could be like this also. So friend, it is quite simple, quite easy. Now I will take the case where this ground level is underwater. It has been flooded completely. So ground level is completely submerged under water. And you want to find out at a depth Z the effective pressure. So this ground is fully saturated, so gamma saturated. And here this height of water above the ground level is ZW, above the ground level, right? And therefore it is Z plus ZW with respect to A. So therefore total stress sigma at A will be gamma sat into Z plus. Now because the water level has gone up, its unit weight is gamma W. So it is going to be gamma W into Z W, and additional pressure due to the weight of water. Now, if I want to find out the pore water pressure at A, if I put a tube over here, the water table will rise up to here. That is, it is going to be gamma W into height of water column will be Z plus ZW. Therefore, the difference of the two will give you the effective pressure at A will be sigma A minus U at A. Therefore, it becomes gamma saturated Z plus gamma W into ZW minus gamma W Z minus gamma W into ZW. This gets cancelled. So it becomes gamma sat minus gamma W into Z. So this becomes the submerged unit weight. So you can write submerged unit weight multiplied by this. So if the water column goes above the groundwater level, the effective stress is not going to change. Even the effective stress for this case, when the water table was here, you got at this level, what was the effective pressure at A for this condition when the groundwater table was here, it was gamma prime into Z. And when the water table goes up, it is gamma prime into Z. So the effective pressure doesn't change in both the case, for this case and this case. Even if there is a flooding of the area, the effective stress is not going to change. So the shearing strength of the ground is not going to change even if there is a flooding of the total area. So this is how you can compute it. If there is a artesian effect and the pore water pressure shoots up, that also you can take into consideration. So let's take some application of this. Let's take some problem on this. And those problems have been asked many times in GATE examination as well as in engineering services examination. It's a very important chapter. So I will take a general problem which is a realistic problem at the ground. So one of the problem that has been considered over here is like this. This is the ground surface or ground level, and here up to 2 meter, at 2 meter depth, you have groundwater tables. So groundwater tables. And then further 1 meter, it is sand. So from ground level up to 3 meter level, it is going to be sand. So first 3 meter from the top, it is going to be sand. And here the unit weight above the groundwater table is 16 kilonewton per cubic meter. And below the groundwater table, the saturated unit weight is 20 kilonewton per cubic meter. And then there is clay. The clay height is 5 meter. And it is completely saturated, and the saturated unit weight of this clay is say 18 kilonewton per cubic meter. And then there is sand layer. So at any depth you want to calculate the effective pressure, you can calculate it, and you can also calculate the total pressure, you can calculate the pore water pressure. So if you want to calculate it, the best way is to calculate in a tabular form. And let's say I want to calculate at this level, then it becomes quite simple. Let's say I call this level as AA, this level as BB, this level as CC, and this level at DD. So at each and every level, we can calculate the total stress. Let's say at A, what is the value of total stress? Value, it will be gamma T multiplied by 2 meters. So up to at A, above that, is there any soil column? No. So naturally at A, sigma A will be 0 because there is no height of soil column over that. Now at BB, that is at 2 meter below the ground level, sigma BB, you can calculate it. It will be gamma T into Z. So it is going to be, what is the height of the soil column here? 2 meter, and gamma T is 16. So 16 multiplied by 2, 32 kilopascal. Similarly, at CC, sigma CC, it is going to be 32 plus, it is here now 20 gamma saturated multiplied by 1 meter. So it becomes 52 kilopascal. Similarly, at sigma, at DD, at this level, you can find it out. It is 52 up to CC plus. Now, what is the value of gamma saturated? It is 18 multiplied by 5 meter. So, Z equal to 5. So, 18 into 5, it becomes 90. 90 plus 50, it becomes 140. So, it becomes 142 kilopascal. So, if you draw the diagram, you can very easily find out what is the variation of total stress. So, total stress variation can be easily plotted over here. So, if you show it, it is 0 here at A, then at BB it is 32, at CC it becomes 52, and at DD it becomes 142 kilopascal at DD, and at CC it is 52, and at BB it is 32, and it is 0 here. So this is the variation of total stress sigma. Now, if I want to calculate the pore water pressure, so U can be calculated. So U at A is going to be 0 because there is no column of water above this. And if you want to come to BB at this level, then is there any column of water? No. Above BB? No. Groundwater table is here at BB. So above that there is no water column, so it is 0. U at CC is going to be unit weight of water multiplied by the column of water, and column of water is of 1 meter. So it is going to be, and let's say the unit weight of water here is given to you as 10 kilonewton per cubic meter. This is the unit weight of water. So it becomes 10. And U at DD will be unit weight of water multiplied by what is the column of water? It is going to be 5 plus 1, that is 6 meter column of water. So it becomes 60. Therefore, you can plot the variation of pore water pressure. So variation of pore water pressure at top A it is 0, at BB it is 0, at CC what is the value? At CC it is 10, and if you come to this level at DD it is going to be 60. So it is going to be from here, this is going to be 60, this is going to be 10. And this minus this will give you the diagram for effective stress. So this is the reference line. Therefore, the effective stress, if you want to calculate sigma prime A, so effective stress at A will be the total stress is 0, this is 0, so this is going to be 0. And sigma prime at BB, what is sigma B? It is 32. And what is UB? It is 0. So it remains unchanged at 32. Now, if you come to CC, then what is the value? It is 52. And what is U at CC? It is 10. So it becomes 42 kilopascal. And sigma prime at DD is going to be 142 sigma minus UW is 60, 82 kilopascal. And this is important. So at top it is 0, and then at BB it has it is not 0, but it is 32. So from here it has become at BB 32, and then at CC it is 42. So at this level it has increased to 42, and at the bottom it is 82. So at the bottom this is 82. This is the variation of effective stress value. In a tabular form, if you calculate, it will be always better. So in a tabular form, how will you calculate? You can just keep it, what is the level at Z. So Z equal to 0, Z in meter. Z is the vertical distance or depth from the ground level. So you can keep it 0 at 2 meter. Then you can keep it at 3 meter. Then you can keep it at 3 plus 5, 8 meter. So you will be coming to this DD level. So 3 meter means CC level, 2 meter means BB level, 0 means at AA. So at these depth, you can find out the value of sigma, you can find out the value of U, and you can find out the value of sigma prime, all in kilopascal. So in a tabular form, very nicely the calculation can be made, same calculation in a tabular form, so that you have clear picture before you and you can plot it like this. So here the groundwater table was here. Now I will be taking the another problem where the groundwater table is going to touch the ground level. So how there is variation, it is same problem, you can take it. So 16, 20 and 18. So we can take another problem. These problems are very popular in engineering services, examinations, also in GATE examination. So the another problem that I am going to explain to you, all of you over here, up to 2 meter, now the groundwater table is going to touch the ground level itself. So groundwater table has come over here, and there is sand up to 3 meter. So this is 0 meter Z depth. It is 3 meter. You can say minus because you are going down, and minus 8 meter. So there is clay, there is sand, and sand is 3 meter, and the saturated unit weight is here 20 kilonewton per cubic meter. And for clay C, the value of gamma saturated is 18 kilonewton per cubic meter. So in a tabular form, I can now calculate. As I have told you, in a tabular form, it will be always better. So depth Z in meter. At what depth? 0. Then take it at 3 meter and take it at 8 meter. Now, first of all, you should calculate the total pressure in kilopascal. So we will be calculating the total stress in kilopascal. So at 0, it will be always 0. And at 3 meter, it will be 20 into 3. So this becomes gamma into Z. So it becomes 20 into 3. So 20 into 3 becomes 60. And at 8 meter, it is going to be 60 plus. This difference is going to be 5 meter. So 5 into 18 or 18 into 5. So 90 plus 60, it becomes 150 kilopascal. So total stress is 0, then 60, then 150. So very easily we can plot it also. And then the pore water pressure in kilopascal, U. Pore water pressure symbol is U. At 0, there is no column of water above that, 0. At 3 meter, it is going to be, let's say the unit weight of water is given to you as 10 kilonewton per cubic meter. So it will be 10 into 3. So it becomes 30. And at this level, the water column is going to be of 8 meter. So 8 into 10, that is 80. So pore water pressure is shown to you 0 here. Pore water pressure at 3 meter is 30, and 8 meter it is 80 kilopascal. Therefore, the effective pressure equal to total pressure minus pore water pressure is going to be 0. This is going to be 30, and this is going to be 70. So the variation of pore water pressure, effective pore water pressure, pressure is going to be 0 here, and then it becomes 30 here. So at this level, 3 meter, it becomes 30. And at this level, it becomes 70. So 70, 30, and 0. This is the variation of effective stress. Similarly, you can plot for total stress and all those things. Now, let's take another example where the water table is going up. So it is completely flooded. So now, in this problem, the water table, not water table, the ground is flooded. And this is the water table now. So because of the flooding, is 2 meter. So above the water plus 2 meter. Now, in this case, the pressure at 0, you can calculate at 0, you can calculate at 3, and you can calculate at 8. So the total stress at 0 is now not 0, but there is a water column. So it becomes 10 into 2. Due to water column, the pressure in the downward direction due to water column will be there. And at 3 meter, this is going to be 20 plus. This is going to be gamma saturated is 20 multiplied by 3. So gamma saturated into the column of soil. So it becomes 60 plus 20, it becomes 80. And at 8 meter, so up to 3 meter, it is 80. And for the remaining 5 meter, so 5 multiplied by 18. So it becomes 90 plus 18, 170 kilopascal. And the pore water pressure in kilopascal can be calculated now. So at 0, there is a column of water of 2 meter. So it is 20 gamma W into column of water above that point. Now at 3 meter, it will be equal to 20 plus 30, that is 50. So the column of water is 2 plus 3, 5 into 10. So it becomes 50. And here at 8 meter, it is going to be 50 already up to this level, plus for the remaining 5 meter. So it becomes 100. So 8 plus 2, 10 into 10, or you can write it 10 into 10. Therefore, the effective stress equal to total stress minus pore water pressure is to be calculated. So 20 minus 20 becomes 0 here, 80 minus 50 becomes 30 here, and 70 minus 100 becomes 70 here. So if you plot it, it is 0 here, 30 here, 70 here. So even if there is flooding, it doesn't affect the effective stress value. So in the previous case, when the groundwater table was touching the ground level, and in this case, when the groundwater table has gone up by 2 meter, there is no change in effective stress. So no change in effective stress, even if the water table has gone above the groundwater table. Friends, we have taken all the cases over here, and in the next video, I will be taking the capillarity effect. What is the effect of capillary water when it shoots up due to surface tension above the groundwater table and saturate the soil mass, how the effective stress value is going to be different, or if there is a piezometric head at any level, artesian effect, then how it will be affecting your effective stress value, total stress value, pore water pressure, all those things in the next video we will. And it is very, very important both in conventional engineering services examination as well as in GATE examination. So I hope and this is going to build a foundation for further deliberation in my next video. Thank you very much.